Alright, this video is going to start with the second section of review for the final, dealing with stoichiometry. Alright, to start with, stoichiometry is a weird word and can be kind of confusing. Basically, what it is it describes the relationship between the reactants and products in a reaction, and it allows you to figure out how much of one thing you need to make another, or vice versa. And the central part of this thing is, or stoichiometry, is a balanced equation. And from this balanced equation, you have coefficients, and you can describe a couple things. You can describe the number of particles, the number of moles, and the mass. Again, using the coefficients of the balanced equation. So let's say we have water. So we have 2H2 plus O2 goes to 2H2O. Okay, so in this case, we've got 2 molecules of H2 plus 1 molecule of O2 goes to 2 molecules of H2O. The same thing goes for moles. 2 moles of H2 to 1 mole of O2 to 2 moles of H2O. For mass, what we would do is we would find the mass of hydrogen, which is 2, and multiply by that 2. So we have 4 grams per mole of hydrogen to 32 grams of oxygen leads to about 36 grams of water. So you find the molar mass of the actual compound, and then you multiply by a coefficient. Now, also using these coefficients, we get something known as a mole ratio. So if we have this equation up here again with the hydrogen and oxygen going to water, basically 1 mole fraction could be 2 moles of H2 to 1 mole of O2. Basically, it's relating the different compounds to one another and using the coefficients. We can do this. The reason why we have these is to help convert between the different compounds, which again is a central idea of stoichiometry. We want to quantify how much product we make from a reactant, or how much reactant is needed to make a product. So let's look at some different types of conversions. All right, the first is going to be a mole-to-mole stoichiometry conversion. In this instant, all we're doing is we're going to take those mole ratios we just talked about, and we're going to convert from moles of one compound to moles of another. Now, before we start any of these types of reactions, or excuse me, any types of these problems, we have to have a balanced equation, which we'll make sure we do. Now, for a mole-to-mole, the generic equation, which we came up in class, is some number of moles that they're given. That's what number value is given in the question. And we're going to multiply it by moles of given using the coefficient here. This blank would be the coefficient from the balanced equation. And then we're going to that's going to go on the bottom, because again, we want to cancel out these moles. And then we're going to put the moles that we want on top. Again, the blank is going to be the coefficient from the balanced equation. Now, on to an example. Burning methane produces CO2 and H2O. How many moles of CO2 is used? That should be used when 10 moles of C3H8 is burned in excess oxygen in the grill. Alright, so the first thing we do is we have an equation. So we have propane, which is C3H8, plus 5 oxygens goes to 3 CO2s plus 4 waters. That is a balanced equation. The way I know is because there's numbers in front. If there were no numbers in front, I would have to balance it. But the first thing you want to do is make sure you have an equation and that you've balanced it. Alright, so we start with the 10 moles they gave us. So that's what's here. So we'd start with 10 moles of propane. Now, looking at the balanced equation, there's not a number here. It's understood to be 1. So that's what's going to go on the bottom. So we want to cancel out these units. So we'll have moles of propane. And then on top, we want CO2 here. Okay, so we look at the balanced equation. We pull out a 3. So we'd have 3 moles of CO2. So now, to actually solve it, we would just multiply 10 times 3, and you end up with 30 moles of CO2. Very basic type of calculation, but it can be tricky. Make sure that when you're doing your moles, you actually put the compound too, because otherwise you're going to get confused on what's where. Alright, now let's add another step to it. Let's say you don't want to go just to moles, you want to go to the grams. Alright, so the first part here is the same as before. You take some moles given, we're going to multiply by that mole ratio. I didn't mention that in the last problem, but this right here is your mole ratio. Okay. And then the new added part is that we're going to have this little bit down here at the end. We now are going to incorporate molar mass of what we want. And the reason we do this is because we want the mass of a compound. So this type of conversion goes from moles of a compound to mass of another compound. And the reason why we have to use the mole ratio is because, remember in the last video I mentioned, moles are universal currency. We can't go from moles of one thing to grams of another without first converting it to from moles of one thing to moles of another. It would be like going from pounds to, I don't know, francs without going through the euro. That's just a hypothetical thing, but the euro would be our mole. We'd have to go from one to another. Alright, so let's look at an example. Determine the mass of sodium chloride when 1.25 moles of chlorine gas reacts vigorously with excess sodium. Alright, so let's look at our equation. We've got two sodiums plus Cl2 goes to 2 NaCl. Alright, first thing we gotta do, a lot of times the first thing I do is if I need a molar mass, I'm gonna go ahead and calculate it. So let's go and calculate the molar mass of sodium. So we take the mass of sodium plus the mass of chlorine, and we end up with about 59 grams, 58, 59 grams for the sodium chloride. So to start with, we take the moles that they gave us, which is 1.25 moles of chlorine. Then we use our mole ratio, okay? Again, there's no number here, so it's understood to be 1. We want to mark out our moles of chlorine, so that means moles of chlorine are going to go on the bottom. We're going to put a 2 in front of the sodium chloride because there's a 2 there in the balanced equation. And then we're going to finish by adding on the molar mass. Now, here in this case, the moles are going to go on the bottom because we want to cancel it out from the second fraction. Remember, the number here always goes with the grams. Always goes with the grams. So now what we're going to do is we're going to multiply and divide. In this case, just multiply, and we get 146 grams of sodium. So it's not really that tricky. All we did was add on molar mass to the end. Again, make sure you follow your units so that they cancel out like I've just shown. Alright, our final and most complicated stoichiometry is going to be a mass-to-mass stoichiometry. This is when you start with the mass of one thing and you're asked to convert to the mass of another. Again, we have to go through moles because that is our universal currency. Alright, so here we go. We start on the far left here. We're given some sort of grams of a compound. Now, here's the new part. We're going to divide by the molar mass that we're given. So this is the compound we start with. We find the molar mass of that. We're going to go back, and this is our mole ratio again. Again, those blanks are going to be from the balanced equation. Okay, mole ratio. And then we end with the molar mass of what we want. Okay? So let's look at another example. Ammonium nitrate produces dinitrogen oxide and water when decomposes. Determine the mass of water produced from the decomposition of 25 grams of solid ammonium nitrate. Alright, so we've got ammonium nitrate goes to N2O and H2O. Okay, so first thing we're going to do is we're going to find the molar mass of everything. Alright, we need molar mass in this case of both things, so we're going to find the molar mass of ammonium nitrate first, since that's the first compound. We have 2 nitrogens, so twice the mass of nitrogen. We have 4 hydrogens, and we have 3 oxygens. Okay, that's going to give us a mass here of about 80 grams per mole. For water, we've talked about this one before. It's 2 hydrogens and 1 oxygen. By this point, you guys should know that's about 18. We've done this a lot in class, so that shouldn't surprise you. That's 18. All right, so here we go. Let's set this up. We're going to start with the grams they gave us here, which is 25 grams. We're starting with ammonium nitrate, so that's going to be the one we start with. We're going to put, this actually should be flipped here. I do apologize. So in your notes, you might want to change that, or I will actually change on the slide afterwards. The mass should be down on the bottom, because right now this doesn't work. So we should have the molar mass on the bottom here. So this should read, so let me mark that out. This should read 1 mole on top and 80.06 grams on the bottom. I do apologize about that. So in your notes, it should be correct. All right, so then we can mark out our grams here. We're left with moles. All right, now we go to our mole fraction, our mole ratio, excuse me. So we have 1 mole of ammonium nitrate. So if we go back a previous slide, you notice that we have a 1 here, and we're going to have a 2 here in front of the water. So here we go. We've got a 2 on top. We can cancel out those moles over there. And then we finish by having the molar mass of water. And again, the molar mass is going to go on top because we want to end with grams. Okay, let me double check and make sure that this calculation is right. Because I'm afraid that I may have messed it up when I messed up the ordering. No, I got the calculation right. So if we multiply and then we divide, you end up with 11.2 grams of water. Again, I do apologize for the switch up on that. It should be changed in your notes. So we have 11.2 grams of water. So we start with the grams of ammonium nitrate, we divide by the molar mass, we multiply by the mole fraction, and then we multiply by the mass of what we want, which in this case is water, and we end up with a mass. Alright, that is the basics of stoichiometry. So now what we're going to do is we're going to take those ideas and we're going to apply it to different circumstances. The first thing is something known as a limiting reactant. Now, when we did this in class, we did it with s'mores, I believe. Yeah, we did it with s'mores. And so what I gave you when we did this in class was I gave you a graham cracker, I gave you a marshmallow, and a piece of chocolate. Okay? So this is graham cracker, marshmallow, and chocolate. Alright? And so the 3 together, actually you had 2 of these, together equals a s'more. And what I asked you to do as groups was to figure out how many things you could make and what was limited. Well, for each one, I basically left off 1. So let's say that you did not have enough marshmallows to make, let's say we had 4 people at your table, you only had enough to make 3. So in that case, the marshmallow that limits how many you can make, is known as your limiting reactant. This happens in real life in chemistry. If you've got a reaction going, you're not going to have, unless you go through and calculate, you're not going to have equal amounts to completely react. So one thing is always going to be less than the other, and we can actually figure this out mathematically, which one would be the lesser of the two. Okay, so the one that limits the reaction is known, surprisingly, as the limiting reactant, and the other thing is known as the excess reactant. If we have more than 2, you have 1 limiting, and then you have everything else is excess. There's no middle ground. It's either limiting or excess. All right, and so what you have to do here is you have to take the mass of whatever they give you, and you have to convert it to the same product. Now, there's only one product, that makes it easy. But you want to convert it to the same product, because what you're going to do is you're going to compare. So, in the example we have here, the reaction between solid white phosphorus and oxygen produces solid tetraphosphorus decooxide, P4O10. Determine the mass of P4O10 formed if 25 grams, so we start with 25 grams of phosphorus and 50 grams of oxygen. All right? And they give us a balanced equation. P4 plus 5O2 goes to P4O10. Now, what we're going to do is we're going to take and we're going to find the molar mass of everything. because we're going to eventually need all of those molar masses. So we're going to start by multiplying by 4 times the mass of phosphorus, and you get 124, give or take. For oxygen, this is oxygen here, you're going to get 32. And then we're going to do for the P4O10, 4 times phosphorus and 10 times oxygen, and you get about 284. Alright, so the first thing we want to do before we answer the question is we've got to figure out, based on what we started with, how much product each forms. In this case, we only have one product, so it doesn't really matter which one we go to. If you had 2 products, again, it doesn't matter which one you go to, as long as you go to the same one. A hint though, if they ask for the amount of product formed for a particular product, it's always handy to go to that product, because then it's less work. Alright, so we're going to start with 25 grams of phosphorus, because that's what they tell us we start with. Now, here's the trick. This is basically going to be a mass-to-mass stoichiometry. So we start with our 25 grams. We're going to divide by the molar mass here. So we're going to get rid of our grams, and that will leave us with moles of phosphorus. Now using the mole ratio, if we go back here, it was a 1 to 1 ratio between the phosphorus and the product, which is what you see here. We get rid of our moles, we get rid of our phosphorus. Now we want to know the mass of the product, P4O10, so we multiply by the molar mass, and here in this instant we're going to make about 52 grams of the product, 57.2 grams of P4O10. Alright, so that's the first one. The second one, we're going to start with 50 grams of O2. Again, we're going to do a mass-to-mass conversion to go from the grams of oxygen to the the grams of P4O10. We're going to the same product. So we divide by the molar mass to get rid of grams. We then are going to multiply by the mole fraction. So we're going to get rid of our moles and our oxygen. We have 5 moles, so if we go back here, we have 5 moles of oxygen to the 1 mole of product. And then we're going to multiply again by the molar mass of the product. Okay? And in this case, it gives us 88 grams of P4O10. 88.7 grams. Now, if you looked at the two, the first, let's go back here. Excuse me. So here we have 57. So basically the numbers we have to compare is 57.2 and 88.7. Well, obviously this one's smaller. So therefore this is P4, this is O2. Our P4 here is going to be our limiting reactant. It creates less product, so it is a limiting reactant. It's going to limit how much product we can make. By default, O2 is our excess, all right? And to answer the question, the limiting reactant, again, is the most amount of product we can make. So that means 57.2 grams is the maximum we can make. So the answer to our question is 57.2 grams of P4O10. So with this type of question, we're taking the idea of mass-to-mass conversions and we're applying it. On a rare occasion, you may see a mole-to-mole or a mole-to-mass, but for the most part, these are going to be mass-to-mass. So you take and you convert both reactants, or 3 reactants, or whatever number of reactants you have, to the same product, and the one that creates the least amount of product is going to be the one that is going to be the limiting reactant. And everything else is excess. 1, 2, 5, however many. Alright. Along the same ideas of this is percent yield. So limiting reactant we can basically look at and figure out which of the reactants is going to limit our reaction. Percent yield is a gauge of how well a reaction went. And we have 2 terms that go with percent yield. First is theoretical. In the name, how much, based on what we started with, should we end up with? So this is going to be, where's my pen here? Okay, this is what we should end up with. Okay, the actual yield is what we do end up with. Alright, this one here is going to be a calculation. the theoretical, it's actually often a mass to mass. And the actual is going to be given. It has to be given. Okay, so it has to be provided in the problem. So, we clear this off. So theoretical is what you should end up with. Actual is what you do end up with. It's what's given. If you run the experiment in a lab, you get a measurement. The only calculation that may come from an actual yield is if they give you like the before mass and the after mass, you have to subtract the difference. But again, it has to be real data. It can't be a number that you start with or something that you can calculate. And to find the percent yield, you take what you do end up with divided by what you should end up with times 100 to get in percent. So it's the actual divided by the theoretical times 100. So let's look at an example. Alright, zinc reacts with hydrogen chloride to produce zinc chloride and hydrogen gas. Alright, that's shown here in that in this equation here. If 25 grams of zinc are used and the reaction yields 0.68 grams of H2, calculate the percent yield. Alright, so we know we start with 25 grams of zinc. We know that we produce 0.68 grams of H2. This is our actual yield right here. Alright, what we have to do is we have to calculate our theoretical. So, to start with, we're going to figure out what the molar mass of H2 is, which is 2 times 1 basically, so it's 2. And then we just look on the periodic table and pull up the molar mass of zinc, which is around 65. And we're going to do a mass-to-mass conversion. We start with 25 grams of zinc. We're going to divide by the molar mass of zinc to get to moles of zinc. We're then going to use the mole ratios, okay? So here we have a 1-to-1 ratio between the zinc and the hydrogen. We also get rid of the zinc. We're then going to multiply by the grams of hydrogen, and that will end up with 0.77 grams of H2. Now, that is our theoretical yield. It doesn't ask for it, but you have to find it. A lot of times these types of questions will ask for it, but in this case it didn't, but we had to find it first. That's the harder part. Now let's just plug and chug, meaning we're going to take our actual yield, which is the 0.680, and we're going to divide it, but we just calculated 0.77 grams. And then we're going to multiply by 100, and we're going to get about 88% yield. That means that 88% of what we started with is what we ended with. So we got about 88% of the product. That's actually not bad. You want around 90 or above, but 88% is not horrible. Okay, again, this part here, the trickiest part is the theoretical. The percent yield is actually the easier of the parts. Alright, that concludes this portion of the review. Our next video will focus on Unit 8 and states of matter and energy.